When we think about factories, many of us still think about assembly lines and heavy machinery. As Terry was describing, that's all changed. New technologies like robots and 3D printers are changing both how we make things and what we actually make. So to kick off our conversation this morning, we'll look at the future of factories with two masters of innovation. If you do a quick search on Ken Goldberg, and the list of what he is long: artist, writer, inventor, researcher. He doesn't fit into any neat little box. If you called him professor, he would probably answer. He teaches industrial engineering here at UC Berkeley, and he also directs the People and Robots Initiative through the Center for Information Technology Research in the Interest of Society, or more simply, CITRIS. You can see the branding on the front of this podium, and that's because this is actually the home of CITRIS. Saul Griffith has been called an invention engine. He won a MacArthur Genius Prize, has founded many companies, and is now the CEO of Otherlab. On the About page of Otherlab, it says, "We are mischievous scientists, practical dreamers, working on making the world what it needs, the way it needs to be." And his team often starts its work by asking the question, wouldn't it be cool if? So here with Saul Griffith and Ken Goldberg is someone no robot could ever replace. My colleague, the Atlantic's Washington editor-at-large, Steve Clemons. Steve will lead the bulk of the conversations today. Steve?
The bulk of them, all of them, right? Yeah, all of them. No, it's good to be with all of you. This is the kind of group I like. We're going to be able to have time. We'll give you all medals or T-shirts or coffee mugs if you stay with us through the day. And we're going to have an intimate conversation with all of you as we go on. And it's great to be with both of you and talk about the future of, it really is beyond just a factory floor, but industrial entrepreneurship. And both of you, I mean, we were just talking in the back that you want to give up your job as CEO and do sort of janitorial. Is there a MacArthur grant in that?
I hope so. I often joke with my employees when they ask me what I want to do when I grow up. And I want to sweep the floors of my factory. And they don't believe me. But it certainly would be a more fun job than CEO.
So Ken, Saul wants to sweep the floors. One of the areas that we've been.
I don't want the robot to
I think that's a good Zen sort of practice. I was just reading about the idea of modesty and CEOs. That modesty is actually very important.
So modesty is cool, but do you see the future of Saul Griffith 5 years from now, 10 years from now, sweeping the floor, in a kind of pining for the past next to a robot that's sweeping the floor?
Maybe I could see him. I could see him with sitting there in the lotus position, meditating while robots are sweeping around him. I could see that happening.
So again, you're here at UC Berkeley. Why don't you take us down the path you've had, and thank you for this, for helping to host us as well, and this fantastic site over here. I'm really into the cyborg beetles. I don't know if you've seen the cyborg beetles, but they are really fascinating.
Oh, over there in the museum?
Yes. Do you not know
they haven't
about the
escaped
cyborg?
yet, no.
Yeah, they haven't escaped. These are things you can put a little chip in and have them fly where you want. Are there human applications on the way?
I don't work on that particular project, I have to say, but that, yes, there's a lot of interest in this kind of hybridizing, where we're thinking about really combining the human and machine together. And we really see that there's a lot of possibility here of trying to figure out what are the best skills and abilities of both. And in particular, machines are very good at lots of things, precision, repetition, but they're extremely bad at any kind of creativity or insight, intuition. Right? So that how can you start combining the best of both? So you have systems where their intuition can be very helpful at certain points, and so you want the robot or the automation system to be able to understand or in some sense recognize that it needs the human, and then call in for help.
Interesting. So look into your crystal ball for a minute. I'm going to ask Saul to do the same thing and take us down this road of what you see as the future manufacturing enterprise. What does it look like? What are the factors that are going to change dramatically in the next 5 to 10 years so that it's not our parents' factory anymore, but something completely different?
Saul, you want to go first?
So into the crystal ball. Actually read a wonderful article on Japan Times this morning about Toyota, who have done a heroic amount of automation with what we all know of as the sort of stereotypical industrial robotic arm, welding its machines. And
of course, Toyota started out at the very beginning as a loom manufacturing company. Did you know that?
And Nokia was a rubber boot company.
Right.
So Toyota have discovered that if you do sufficient automation, and they had relentlessly tried to automate every single process, you stop improving at some point because the robots don't learn. So they're actually now paying these people, I can't remember the Japanese term, but it roughly translates to gods, who use very traditional manual processes to forge crankshafts and to make the individual parts, so that those humans can then figure out how to further optimize the automation lines.
Right.
So this is, I think everybody fantasizes about a factory that you put stuff in and stuff comes out and there is no labor in the middle and it's clean and cost effective. But I think that's the first sign I've seen of, oh no, there's a limit to that, and it fails because the robots can't yet learn how to improve the process. So they're limited by the thing. So I think that's an interesting, sort of that tempers my enthusiasm for robotics. I do think we're going to see increasing amounts, but if I had to characterize where robotics and industrial automation is right now, we have machines that are overweight, blind, stupid, slow, and weak, which really means you read the headlines and you see the videos on YouTube of these industrial robots, but honestly, if the car isn't moved into the exact position, the robot will fail because the robot can't see where it's welding. It's just imagining that the car has been put into place. So all of these industrial lines, almost without exception, run on a sort of record macro and playback model. So they bring the car in, they use a huge amount of effort to lock it down exactly in place. They record the movement of the robot going there, and then they hope to just repeat that every single time. So this is what I mean by the robots are blind. They can't see what they're doing. They can't work together. So you place them so that if they do an errant move, they don't hit the one next to them, because then you take two things. So, and then an industrial robot, typical industrial robot that can lift 30 pounds at arm's length. So you can imagine, we can all roughly lift a 2-year-old at arm's length. It hurts a bit. I did it this morning. It takes me 100 or 200 watts of power to lift that 30-pound thing at arm's length. It takes these industrial robots about 10 kilowatts of power to move that 30-pound load. So this is what I mean by they're weak and they're power hungry. So they use 10 to 100 times more energy than us. And we fundamentally need to improve that, otherwise they will never be mobile robots on the factory floor because they need a giant cable of electricity in the back. So I guess I'm not giving you a terribly optimistic
No, you're a real cynic.
I see all...
I thought you were going to be fun.
No, I think we should be realistic. Like, what are the problems and the challenges? So I think by defining these, you then be like, okay, so
I have a quote here from you. It says that my team sent me. It says, even if electromechanical robots were twice as good as they are today, they still wouldn't be good enough. And we don't even know how to make them twice as good, said Griffith. You have to change the game. So one, I have two questions. Is one, how do you see changing the game? And why are you thinking about 2 times? Isn't when we have synthesized artificial intelligence and lots of other kinds of capacity, imagine sort of the Bill Joy concern about increased capacity in everything. Aren't we talking about 100 times, more than 2 times at some point?
I think Ken set you up to ask this question because this is going to be where we get to have a debate around untested ideas. First of all, I neither believe in the singularity nor exponentials. They're mathematical curiosities.
All right, could we agree on that?
There we go.
Right, totally.
So, let me illustrate with an example. If I feed... Ken was eating a buttery croissant earlier that has roughly 36 megajoules per kilogram of energy in that croissant, which is magically roughly the same amount of energy as there is in a kilogram of diesel or gasoline. Ken converts that to mechanical work to lift his 30-pound child at roughly 25% efficiency. So he gets 25% of that 36 kilojoules. So he has an amazing sort of strength to weight kind of ratio, if you imagine. If you take any robot, and it doesn't matter how you design that robot, whether you do batteries, which have 1 or 2 megajoules per kilogram, going into electric motors at very high efficiency, they still end up roughly 1/10 or lower than Ken. If you use a diesel generator and an electric battery and to then, all of the things, and it doesn't matter whether you do hydraulics or pneumatics or electromechanics, you still end up kind of a factor of 10 short of what I would call mammalian, meaning can move as fast as we can go as efficiently as we can do the things we can do. So we're not going to get any of the mobile robots of Hollywood's dreams because they need this giant cord, or they'll be mobile for 30 seconds. So as long as you can run.
I often need a techno-skeptic on panels that I do. In
this is not techno-skepticism.
Yeah.
This is like the raw physics. I really think it's dangerous to paint this as techno-skepticism. I think
it's
really
techno-realism.
No, this is actually how you identify what the real
Right.
opportunities are and what the business world of the future looks like, rather than reading fantasy science fiction, which is people do.
Or
Ken?
actually, many mainstream publications, right? I think there's this extreme optimism that's happening right now. That's some people have characterized this as Moore's curse.
Right.
Moore's law.
But you did tweet out on May 21st, Ken, exciting Cal story by John Markoff, new approach trains robots to match human dexterity and speed. You can feel the enthusiasm just ripping out of that tweet.
I'm not unbridled pessimist either, but and that actually is a really exciting result by my colleague Peter Abil, who's here on deep learning. Well, we can talk more about that. But so I see a lot of potential, and there's a lot of interesting problems that can be addressed, and specifically these new techniques that combine analytic with very, very high parameter systems like neural networks in deep learning have potential to make a big difference. It's really important, though, if we look at the state of the art, there's this fear that because Moore's law has had this exponential growth, that the same thing is about to happen, that we're going to solve these problems and that robots are going to take over. And Saul's absolutely right. We have to be really skeptical about that.
They might be geniuses. I think that we'll make more progress on the robot's brain. So they may be evil geniuses even.
Right.
But the good news for us as humans is we're going to be able to outrun them. So like all of the dystopian futures.
Paul Bunyan wins.
Yeah, all of the dystopian futures can't come
Yeah, that's
true.
the headline, right?
Yeah, if you saw the DARPA challenge last weekend.
It's like watching golf.
Yeah, exactly. That was the upside. That was the improvement over watching grass grow. It's now gotten to the point of watching golf. So that shows the level of evolution. But I agree. Also, I think we've learned from that experience that bipedal humanoids are not necessarily the right way to do robotics. That's extremely challenging. It would be nice because we'd like to be able to allow them to go in, for example, to a nuclear reactor and clean up afterward. That's one application where you can see a case. But for almost everything else, it's really not practical and extremely hard to replicate the human model, the human form.
And if we try to use this to answer your original question, how does it transform the factory of the future? I think actually having these very realistic expectations of it then says, and you can, all of the success stories in robots kind of fall out of from reaching this conclusion. So anywhere where you can structure the environment and have the robots on wheels. And so this is why they've done well with Kiva systems in automation, where they lock down everything into known locations and they have efficient robots on wheels. Because wheeled locomotion is very, very efficient. This is why it's easier to ride a bicycle than to walk somewhere. This is why autonomous cars are a kind of a very interesting application of robots, because the car is already such a horribly inefficient machine that you can kind of ignore the energy problem, and it's also running in this hugely structured environment, namely roads, and so there's very big opportunities to win there, and really all the innovations you need are not in the cars or even in the sensors so much, it's just in the algorithms to run it. So you can expect that we'll make a lot of progress there very quickly. But yes, this idea that we'll have bipedal robots walking around our home washing our dishes. So it's actually all the things that we really want robots to do are the hardest problems. I had to tell you the hardest problems for robots. It's like wash my dishes, sew a T-shirt, right? Every single who believes that any of the items of clothing they're wearing were completely made by machine? Here. It's right? This is a little bit shocking. I mean, you're a well-educated audience, so nobody guessed incorrectly. Often everyone believes or wants to believe that all of our items of clothing are made by robots, because it's horrible to believe the alternative.
Made in sweatshops
but they are all made
China
in
places.
sweatshops in China.
Yeah.
And so then you were like, okay, well, you should build a
We have
sewing
a lot
machine.
of Chinese folks watching online live right now.
Well, it's actually moved out of China into the rest of Southeast Asia. So it's
right,
actually now Vietnam and Myanmar and Bangladesh, and it's like it's falling down the hierarchy. So then you're like, okay, so we should build sewing robots, and I think you could. You could probably single out the American trade imbalance with Southeast Asia if you could just do T-shirts and underwear in some autonomous fashion. But the problem is that if I have some of these industrial robots, it costs me a couple of dollars an hour in electricity to keep them moving because they're so inefficient. There are 2 billion people who are working for $1 or $2 a day, so they are just as strong and they're faster and they have a brain, they have a vision system, and they're way faster than robots. So, and there's an infinite supply of that labor.
So you helped co-author a cartoon on technology for kids. Can you put all this in that?
This might be a little dark, but I think this is realistic, right? So humans are so efficient as robots that you need to temper your enthusiasm for some of the things that we would.
Well, let me just be, so as I think about technology, whether it's in the health area or energy, and I've been in a few Siemens plants and they build sort of large generators and engines and they build everything. But when you get in, it seems to me that both software advances and then other kind of machinery and industrial advances are essentially to crunch out variation, right? So a lot of what you're trying to do when you automate something is to create efficiencies and to crunch out variation. I often ask when I do an education program, is there a program that can crunch out the variation in teachers? Do you really need teachers to teach? It's a bad subject to go into here, but when you begin thinking about the future, yeah, I mean, you're a teacher and a scientist, right? So at least you've got half your job in the future.
Which half? Actually, no. When you say crunch out the variation, right? That's an interesting term, because one thing we haven't talked about, which is part of this term that we're hearing a lot of, Industry 4.0, that Siemens actually has been involved in, or Industrial Internet, which is GE's version of this, is the other big ingredient that's changing is the role of the internet. That really starting to see machinery in factories being linked together and sharing data and software, where that actually, I think, is something where a cause for optimism, that we are just at the very early stages. We call it cloud robotics, which is where the idea that robots, we've always had this assumption, again from the anthropomorphic sort of bias, that robots have to carry all their processing on board. And only recently we've started realizing, well, actually they don't. You can, almost everywhere you have robots, you have access to the internet with wireless or wired connection. And so you don't have to carry all the memory. You don't have to carry all the processing. All that can be done remotely. And that has two advantages. One is that it allows you to have far more resources than you could otherwise. But second of all, then robots can start sharing information across machines. So then they can start fine-tuning based on all the different conditions that they encounter. So this is where, from everything from individual sewing machines to the dishwashers out there and everything else, everything so far has been isolated and essentially like an island. And it gets made in the factory and then put out and then it runs and then it never gets tuned after that. But you can imagine where nowadays, at least for almost all software products, they're getting downloads of upgrades and new versions of software all the time. But you can take that at a much finer grain level, where they're actually looking at conditions of every single instance. Those are all coming back to essential sites, processing that to learn better parameter fitting, and then those are all being downloaded back into the machines. So we're getting much better performance and be able to handle this variation that you're talking about.
So Saul, one of the ways we've stacked the deck today in today's program is thinking a little bit more about this industrial dimension of innovation as opposed to what's going on in software. And there's this debate going on whether Silicon Valley is hitting below its weight, that it's focused on the wrong things, that it's producing software type advances, but it's not doing what David Packard and other sort of large-scale, Noyce and Gordon Moore and others did, thinking about things that were sort of big industrial strategic leaps. And is part of the answer what you just shared, that those big industrial leaps are much harder than people think, and so they're taking the path of least resistance?
Silicon Valley is hugely optimized to spend a small amount of capital for giant returns, which eliminates you from playing in anything that's a capital equipment intensive industry. So I think I am also disappointed that Silicon Valley or the economy at large does not place bigger bets on transforming the energy system, transforming manufacturing to make it cleaner and more environmentally friendly,
Right.
et cetera. But to expect traditional Silicon Valley to do that is to misunderstand what it has been optimized for over 50 years.
So let's both of you just jump forward into that. I mean, that's a fascinating hole to jump into. So we're at UC Berkeley. You work here, and yet you're an entrepreneur as well, and I assume you're tied into this place as well. Both. I mean, you've invented like 20 companies. You've co-founded, I saw, about 20 companies that make fascinating things. But how do you get back to those bold bets, the big bet strategies, and reflecting on what universities can do, what other commercial properties can do, what can government do? What's not happening that needs to happen to be more transformative? Because it sounds like you want it to be.
Well, one thing, I mean, one counterexample I would have to say is probably Tesla, right?
Right.
I mean, they're innovating big time, and in both the products and the production, and the whole concepting of, and they think big. I disagree with Musk a bit about the fear of the singularity part, but
Right.
everything else I'm very impressed by. I think the idea is as Saul's saying, is taking risks. And it's one thing that I think universities are well set up to do, both because of the tenure system, the various approaches that let you take a chance, do something that may fail.
How many failures have you had at Berkeley?
Uncountable.
Yeah.
I mean, I have to say it's a great place. It's very forgiving for that, and I've had lots of things that don't work out, and hopefully I'll have many more failures coming up. But I think that that this is one thing that industry is different, where there you can fail, and you can lose your life savings, you can lose your job. Here in a university, and this is what we're always talking with students and postdocs, is that in a university environment you can take all kinds of chances simultaneously. You can have different projects going on and trying different things out. So I think that idea of risk taking, I hope you would agree, is actually critical. You do it in the commercial sector.
Yeah, I think universities have an increasing role in that, and I actually wish universities were even riskier and bolder. But there's really a limit to what a university can take on, because roughly everyone is a highly intelligent, autonomous anarchist. So,
especially at Berkeley, yeah.
Especially at Berkeley. And so it's at a university, it's heroic to get 6 people marching in the same direction.
Yeah.
And 6 people can do amazing things marching in the same directions, which is why you see some truly astounding things come out of university. But if you wish to transform the automotive industry, you need an unbelievable amount of capital, which, the amount of money that Tesla has thrown. I agree that Tesla is super impressive. When you actually go, and I've gone and looked at the robot line, there's nothing that their robots are doing that industrial robots weren't doing 20 years ago. They just had the opportunity to do a clean, fresh production line. So they just threw a few more at them and did
Let me
it.
open to all of you. Questions, comments, thoughts. Join the conversation.
I think we sort of need, I think what we find, so I'm sadly attracted to energy problems and manufacturing industry problems.
Right.
I should do software because of the things that I just said about Silicon Valley. But really, to get these things to come into these markets, you need partners who have the capital to go after those problems. And so I think the Siemens of the world, the Fords, the GEs, are in fact probably the only. The Tesla is the unicorn, as they say in Silicon Valley. It's going to be the exception. The reality is, if you want to rapidly scale interesting, new, transformative automation, the likely pathway is, small group of people do some great work at Berkeley or at Otherlab or at Stanford or somewhere, is absorbed into giant, capital-intensive, highly operational business like Ford or GE, and they bring it to market in a big way. I don't see enough of those big companies taking that next step on the risk. And I think that may just be the dysfunction of where the markets are at the moment or something. But I think that's where the innovation system is failing. We're not quite having this. The early risks are being taken and they're being run and people are doing good things. But then that next step is not happening enough.
I like your socks, by the way.
Thank you.
Let me open the floor. Yes,
Risk,
right here.
high-risk socks.
Yeah. Maybe not in Berkeley, but in DC, those would be very high risk. Yes,
Hey,
yes, sir. Hi.
great conversation. A couple questions. The vast majority of manufacturing in the United States is really small and medium-sized enterprises, 300 employees to 500. Can you comment on the potential of both automation and robotics and customization in having those kind of industries just take off again? Because they've been kind of stuck for years and losing employment.
Well, actually, it's a great question. There is a movement now, and you're probably familiar with Baxter robots, right, where they rethink robots, where the idea is to develop low-cost robots on the order of $20,000. Typically, they've been $50,000 to $100,000 just to get one robot. And it's because it's very high precision motors and very high precision gearing. Here, you start to shift that, where you're using lower cost components, but you try and compensate in software. I mean, I think it's really interesting with Saul's doing this work with soft robotics. And similarly, you lose precision, right? But you gain in lots of other directions, in weight and energy and cost. And this is where the opportunity is, where software can have enormous advantage, right? You have to be able to close that loop, so you're not just doing these blind motions, because you can't actually, if you make the same command, you won't get to the same point in space. So that's where you have to have sensors. And fortunately, there's been enormous advances in machine vision, in 3D sensing, and yet they're still highly noisy, those systems, those sensors. So we need techniques to be able to close the loop and do control policies that are reliable.
Saul?
Underline exclamation point, closed loop. So all of the industrial robots and CNC machines we have today run open loop, meaning they're blind and unfeeling. But as we close the loop in software on these things, we're going to see real transformation happen. But the transformation in the industry, in this sector that you're talking about, is really, really happening. It's far fewer of these industrial robotic arms, because they really are limited in their application. But if you look at Haas or any of the CNC manufacturers, they are selling so many of these machines into these places. The underappreciated thing that's also supporting a return to American manufacturing is just the incredible efficiency of the logistics, infrastructure, trucking, et cetera. That's getting more efficient. That's a software thing. So really the great story in that is, it doesn't sound like the robots we see in Hollywood, but it's great CNC machines and it's great software doing better logistics. We will see, as we close the loop on this software, more of these other robots coming in. I think the other part of your question I find super interesting is customization. We have a project where we're teaching, we built, what's interesting to me, so CNC machines used to be you had to spend $1 million. We now often will design and build a CNC machine. It takes us 1 to 3 months to commission a 3, 4, or 5 axis CNC machine of a completely new category. So we've just recently made a 4-axis metal cutting laser cutter, $100,000 in engineer time, $100,000 in parts. So for a reasonable amount of money for a small business, you can build this completely custom machine that does something great. We designed this one, so one of the things it can do is cut metal tubes really perfectly. We then build some software so that you could walk into my office next week, we'll measure you up, automatically design the perfect optimum bicycle for you, whether you're optimizing for touring comfort or for racing speed. 4-axis machines, cut the tubes, place it into a jig, and the 2 robots go and weld you the whole bike, and you have your custom bike in 1 hour while you wait. So I think you can conceive of this. There's still a lot of hard problems. To actually make that work, we have to solve this closed loop problem, because the tolerances required to make a bicycle are way higher than tolerances required to weld a car chassis. So we actually have to improve.
We are out of time, guys, unfortunately, because I could talk for hours about many things you're doing. But let me just real fast, one of the areas we didn't talk about was 3D printing, and I know you've been working a lot on that as well. Do you have more confidence in the transformative dimensions of 3D?
I have been made famous for saying, if you wish to make expensive, fragile parts slowly and send them to landfill, you should choose to use a 3D printer. So
Oh, that's good.
I think that's actually far too
I
disingenuous.
can't believe you don't tweet. He actually told me that, I had my people go find tweets of everybody, and I found Otherlab, and it says Saul Griffith, and it has there, and he says, wait, I don't have a Twitter account, but you do. But you
Actually,
use it.
the gentleman who
Yeah.
I think tweets for us is in the front row, and he probably just cringed because I said that.
I like it
publicly.
anyway. He doesn't
But-
know we have it. Anyway, thank you.
Yeah.
Keep tweeting.
On
that was a
3D
tweetable
but
line right there.
Just to
Very
close the thought on
interesting,
that, 3D printing is interesting and it is transformative, but it's actually hiding what is really transformative, which is the ability to build custom CNC machines.
Yeah.
So you're going to 3D print a bicycle that has the weight and the strength of this other thing I'm building? No. I come from material science and metallurgy. The properties of every single material we have is a function of what they call thermomechanical processing. So how hot it was, how fast it was cooled, all of these other things. 3D printers live in this static temperature and pressure world that is great for creating complicated geometry, but it's not great at creating high-performance materials. And I think it's a long time before we solve that problem. So those headlines are a great smokescreen for the real revolution, which is in CNC machining and robots.
Although I'll tell you one area where it's actually being very, very effectively used is in healthcare and medicine. So we're using it to 3D print implants for radiation treatment that can be customized to the patient. And I think that area is
Awesome.
So small, fragile, even printed.
No. Well, I mean, that
But
case,
yeah, it still works.
you
Right,
really
still
care
works,
about the geometry
Right.
being specific to the patient. So it's a great
Nice, optimistic thought to end on. So, Ken Goldberg, thank you very much, Professor of Industrial Engineering and Operations Research at UC Berkeley. And Saul Griffith, Chief Executive Officer, Inventor, and Future Janitor at Otherlab. Thank you both very much.
Thank you.